Hello, let's do the homework. So this is review 2 of 3 review worksheets that I'll be making for you. For the first 5 here, depends on how you do the problem, if you're a unit circle person or if you like the 30, 60, 90 and the 45, 45, 90, or some of you do a combo. So if I don't address your needs as I go through these, you can just reach out to me and I'll help you with whatever method you're choosing to use. For cosecant of negative 11 pi over 6, we all have to pretty much sketch negative 11 pi over 6 to find out where it lands. It lands here, it's coterminal with pi over 6 or 30 degrees. So if you're a unit circle person, you're going to grab the y coordinate there, which is 1/2, and then flip it to get 2 because cosecant's the reciprocal of sine. If you like your reference angle here is 30, so you're going to look at your 30, 60, 90. And with respect to 30 degrees, which is across from 1, cosecant is going to be hypotenuse over opposite because it's the reciprocal of sine. So hypotenuse over opposite is going to be 2/1. And then we're going to use positive here because in quadrant 1, all 6 trig functions are positive. Even though the angle's negative, the answer is positive. For cotangent of negative 90 degrees, you can't use a triangle for that one. So we all pretty much have to sketch that, realize it's coterminal with 270, and we grab a point on the terminal side. For cotangent, the definition is x over y. So if we put x over y, we end up with 0. 0 in the numerator reduces to 0. If you had 0 in the denominator, it would be undefined instead. For sine of 4 pi over 3, 4 pi over 3 is here in quadrant 3. If you're a unit circle person, you're going to look at the unit circle. You're going to grab the y coordinate. The y coordinate here is negative radical 3 over 2. If you like your quadrants and reference angles, your reference angle, remember, a reference angle always goes to the x-axis. So we went pi over 3 past pi, so the reference angle is 60. And if we go take a look at our 30, 60, 90, the sine of 60, 60 is over here. Okay, the sine of 60 is radical 3 over 2. And the reason we're selecting a negative for the SIGN is because in quadrant 3, only tangent and cotangent are positive, therefore sine should be negative. So again, please be careful. Positive angle can result in a negative ratio or a positive ratio. It depends on the quadrant. Okay, so don't think a negative angle has to give you a negative ratio. That's not the case. So you could have a negative here and a positive here. You could have a positive here and a negative here. You could also have a negative angle and a negative ratio, or you could have a positive angle and a positive ratio. Any combination of those can happen. What determines the SIGN is the quadrant. For secant theta equals -1, if you want, you can flip that. And if instead of -1 over 1, you'll have -1. So if you prefer to work with cosine instead of secant, you can do that. Now, even if you like your triangles, if you look at your 30, 60, 90, you're never going to get cosine to be 1. And in your 45, 45, 90, you're never going to get cosine to be 1. Tangent can be 1 in the 45, 45, 90, but not cosine or secant. So what we have to do here is work with a quadrant angle. All right, so my students who like the 30, 60, 90, and the 45, 45, 90, if 30, 60, and 45 don't work, you look at quadrant angles. Students who like the unit circle, you're going to be looking for where the x-coordinate is -1 on the unit circle. So since we know it's a quadrant angle, you really only have to check 0, pi over 2, pi, 3 pi over 2. And you can either work with cosine or secant. So my unit circle people, if you like cosine, you're going to grab this right here, the x-coordinate. So the answer is going to be pi. And if you prefer to use the definition of secant, is r over x. So for all of these points here, r is 1, because each of these points is 1 unit from the origin. And if we test r over x here, that's going to be 1 over 1. That's +1. That's not, I'm sorry, I'm looking at secant. So if I'm doing secant right here, if I do r over x is 1 over 1. That does not match. It has the wrong SIGN. So it's not this one. And then if I do r over x, so that's r over x, 1 over 0, that would be undefined. That's not a match. But if I go out here and try r over x, the r is 1, the x is -1, and that's going to give me the -1 that I wanted. So the answer is pi. And you can check down here as well, just to make sure this doesn't work. If we do r over x down here at 3 pi over 2, r over x would be 1 over 0, which is undefined again. So only pi is the answer here. The directions say to give answers from 0 to 2 pi, so that's why pi is the answer. You don't want to give 180 there because it didn't ask for the answers in degrees. It only asked for the answer in radians. Next one, solve for where tangent theta equals -1. So this is going to be, if you're a unit circle person, you're going to go to the unit circle and look for where y over x or sine over cosine comes out to -1. And you can test those out, and you're going to find that there's 2 locations for that. The 2 locations where that happens are 3 pi over 4 and 7 pi over 4. All right, because what's going to happen at 3 pi over 4 is you're going to have, for y over x, you're going to have radical 2 over 2 over negative radical 2 over 2 when you grab the y coordinate over the x coordinate, and that's going to reduce to -1, and that works. Similarly, the ordered pair at 7 pi over 4 will also work. So that's if you're a unit circle person. If you like your quadrants and reference angles, then what you want to do is you want to realize that the tangent of 45 degrees is 1, because SOHCAHTOA is going to give us 1 over 1. So our reference angle is 45, or pi over 4, since the directions say to give answers in radians. So for pi over 4, we want to figure out the quadrants here. Since tangent is negative, we want to be in quadrants 2 and 4. So the angle in quadrant 2 that has a pi over 4 reference angle is going to be pi minus pi over 4. So we also get 3 pi over 4, even though we're using a different method. And the angle in quadrant 4 that has a pi over 4 reference angle is 2 pi minus pi over 4. And that's going to give you 7 pi over 4. So we agree on the answers, even if we do a different method to get there. So you can do unit circle, or you can use your quadrants and reference angles. So your triangles and then your reference angle, and all students take calculus, or some combination of the both. All right. Let's continue on. Next, period and amplitude for this sine function. So notice here I did mix these together. So in the first review, I kept these as separate, 4, 6, 4, 5, 4, 6, 4, 7. Here I've mixed them together to give you some better practice. So for the period and amplitude is going to be the absolute value of the number that's out front. Okay, so whatever causes the vertical stretch or shrink, if there is one, that's amplitude. The absolute value 2/5 is 2/5. For the period of sine or cosine or secant or cosecant, it's 2 pi over absolute value b. We're never really going to have a negative b, so if you just want to do 2 pi over b, that's fine. The b here is the coefficient of x. So the b here is 3 pi. So if I put 2 pi over 3 pi, the pi's reduce, and we just get 2/3 as our answer. Kind of unusual. We've seen it before, but it doesn't happen to us too often, that our period does not have a pi in it. But the reason the period for this one doesn't have pi is because the b value, the coefficient of x, had a pi in it, so that's why it reduced out. For number 7, we want to find the period of this tangent function. For tangent and cotangent, the period is going to be pi over the absolute value of b. So b here is the coefficient of x, and you're going to end up with pi over 5. Now let's get into some graphing. For number 8, we want to graph cosine flipped over the x-axis and move down 2. So cosine looks like this. It's our nice even function that has a y-intercept up there at 1. If you don't remember how to graph this, contact me. We can do a little extra help. I'll remind you how to use the quadrant angles on the unit circle to get that graph going. So using just the quadrant angles on the unit circle, that's how we started when we started graphing sine and cosine. But I think a lot of you remember that cosine just looks like this. So I'm going to start there. Now remember to do your sequence of transformations. There's no stretches or shrinks. There's no horizontal shifts. So we'll do the reflection next. This is a reflection over the x-axis. So it goes like this. Makes that kind of double helix shape. Looks like DNA. And then we want to move down 2. So I'm going to take this critical point and move it down 2. I'm going to take this x-intercept, move it down 2. It's no longer an x-intercept, but it's still a point of inflection. The max moves down 2. And all these points move down 2. And then if you can connect the dots, just try to make hills and valleys because you want to have concavity. You don't want to have straight segments anywhere. Okay, so hills and valleys. And there is my final graph. All right. So this black one is regular cosine. This red one is cosine flipped over the x-axis. And you know what? I think I'll trace over it in a marker just so that it's nice and clear. on my answer key. Here's an orange marker or highlighter. Okay. That way it stands out from the other red graph, so there's no confusion that this one is my final. Okay. And we continue with number 9. Number 9 is to graph a cosecant function. Graphing a cosecant function isn't very different from graphing sine and cosine because remember, we don't transform cosecant. We don't do a vertical stretch of cosecant. What we do is we graph the reciprocal, which is sine, with the same transformations. And the only transformation here is the 2. So what we're going to do is we're going to take sine and stretch it out by 2. So sine usually looks like this. Okay, I think at this point we know that sine goes through the origin, goes up to the right and down to the left. If you do not know how I got this graph, if you need a reminder on that, just email me. It will set up a little extra help and I'll remind you how to get that graph. And then we want to stretch this out by 2. So what I do is I multiply the y's by 2. So when you multiply this y by 2, it's 0 times 2 stays at 0. The y here is 1. 1 times 2 is 2. Here, 0 for the y, so 0 times 2 is still 0. Here the y is negative 1. Negative 1 times 2 is negative 2. And then we have 0 again. Now what happens here is sometimes people think that you're moving the max up 1 or you're moving the min down 1. That's not really what's happening. You don't want to think of it as moving up or moving down. You're multiplying. You're multiplying the y value by 2. Okay, because the vertical stretches by 2. All right, so this one is my stretched out graph. Trying to make it a little darker so it stands out from the original sine graph. And then to graph cosecant, all we need to do is find the points of inflection. The points of inflection for this graph are on the x-axis. They happen to be the x-intercepts. On the first review sheet, we had a vertical shift, so the points of inflection were not on the x-axis, so just be careful. But the points of inflection in this case are on the x-axis, and that's where the vertical asymptotes go. So that's where the vertical asymptotes for our cosecant graph go. And then we put our U-shaped curves. Anywhere that sine has a max, we're going to share that point. We're going to put a U-shaped curve that opens up. Anywhere sine has a min, we're going to share that point and then have a U-shaped curve that opens down. We like to throw the arrows on these. We'd like to approach the asymptotes. So you don't want to just you don't want to go from here and just go straight up. You want to approach the asymptote and then put the arrow on. And our steepness won't be perfect, but it's good enough for what we're doing. And there was a second question here. It says, is the function even, odd, or neither? This function is odd. Okay, so this function ends up being odd because if I spin my paper 180 degrees, it looks exactly the same as it did before. All right, to graph inverse cosine. I know you guys can just look that up in your notes, but to remind you how we know how to graph inverse cosine, what we did is we started with regular cosine because we know it so well. And then we restricted the domain. The domain that we selected went from here to here because that part of the graph will be 1 to 1. It'll pass the horizontal line test. This point is 0, 1. This point is pi over 2, 0. And this point is pi negative 1. The restricted domain that we're using for this cosine graph, so the part that I highlighted in orange, goes from 0 to pi, and the range goes from negative 1 to 1. Now, for the inverse, the domain and range are going to switch. So the domain is going to go from negative 1 to 1, and the range will go from 0 to pi. To get the graph of inverse cosine, we flip-flop the x's and y's. We reverse those ordered pairs. That's a property of inverses. So if 0, 1 is on cosine, then 1, 0 is on the inverse. If pi over 2, 0 is on cosine, then 0 pi over 2 is on the inverse. And finally, if instead of pi negative 1, it's a little sloppy, let me clean that up. Instead of pi negative 1, we're going to have negative 1 pi. And if you want to label those, it's not a bad idea. Oh, but label them correctly. I'm just going to write pi over 2, 0. That's 0 pi over 2. It's not a bad idea to label the coordinates of the endpoints so that they're nice and clear. Because if you don't label them, it can be hard to tell exactly where that is. So by putting negative 1 pi, we know where that is. And finally, to do our graph, we want to reverse the concavity. So from left to right, this is concave down, concave up. So we're going to reverse that. Instead of down and then up, we're going to go concave up and then concave down. And that'll match the graph that you have in your notes for inverse cosine. For the domain and range of inverse tangent, you could look that up in your notes, but for a little bit better review, let's think about regular tangent. Regular tangent looks like this, kind of reminds me of x cubed. And it's not one-to-one, of course. So what we do is we just take this piece in the middle for the restricted domain. So for regular old tangent, not the inverse, the restricted domain goes from negative pi over 2 to positive pi over 2. And we have to use parentheses because that's where the asymptotes are. Pi over 2 is not even in the domain of tangent, so it certainly can't be in the restricted domain. All right, so that's why these are parentheses instead of brackets on the restricted domain, because pi over 2 is not in the domain of tangent because there's an asymptote there. So there's no way we can put it in the restricted domain. So now that we have the restricted domain and the range for the regular tangent graph, for tangent inverse, we just switch those. So the domain is negative infinity to positive infinity, and the range is negative pi over 2 to positive pi over 2 with parentheses. Okay, next one. We want to write an equation for this. We're going to assume no horizontal shift. So the way I like to do this is start at the y-intercept. Since the y-intercept is a point of inflection, that means I'm dealing with a sine graph of some sort. If the y-intercept is a max or a min, then you're dealing with a cosine graph, as long as there's no horizontal shift. The next thing I like to do is find the midline. Since my maxes are at 3 and my mins are at -3, my midline is 0. That means there's no vertical shift. The next thing I like to do is find the amplitude. The amplitude here is 3. If the amplitude is 3, since that's the absolute value of A, that means that mathematically A could be 3 or -3. To pick whether we want to put 3 or -3 out here, we check for a reflection. Has there been a reflection? Yes, because sine usually goes up to the right, and here it's going down to the right instead. So we're going to pick that because there's been a reflection over the x-axis. I just dropped my white out on the floor. That's what that noise was. So I'm going to put -3 here. And then the last thing to check is to check for the period of the function. So for the period of the function, we want 5 critical points. And I did not mean to make this as tricky as I did, but we'll handle it. So 1, 2, 3, 4. I meant to extend the graph so you could see the 5th one, but I'll go ahead and put one here. We'll handle it. All right, so this is a little trickier than I had intended, but we'll survive. So we have 5 critical points. This one is at -pi, and this one's at 3 pi. So how far is it from -pi to 3 pi? That's a distance of 4 pi. So the period is 4 pi. The period is usually 2 pi. Since this is longer, that's a horizontal stretch. To find out what b is, we take the formula and we set it equal to the actual new period. I'm going to run out of space, so I'm going to just move this information here so I don't have to redo the whole thing. All right, so we take the formula for the period, we set it equal to the actual period, and then we can cross multiply to solve. 2 pi times 1 is 2 pi. B times 4 pi is going to give us this. And then to solve for b, we'll divide by 4 pi. The pi's reduce. 2 over 4 is 1/2, and that's what I want to put here for b. So my final answer is y equals -3 sine 1/2 x, or -3 sine x over 2, if you'd like to make it more compact. And I'm just going to rewrite this information back down there. Okay, so that is number 12. Let's continue to number 13. Number 13 is a tangent graph. When I give you a graph of tangent and ask you to write the equation, I only did that with one transformation because sine and cosine are easier I won't say easier. Sine and cosine have more clues. We have the midline, we have the amplitude, and we're more familiar with these graphs. So I can give you a graph for sine or cosine that has quite a few transformations in it, like a reflection, a vertical stretch, and a horizontal stretch, and you can actually figure it out. For tangent, that would be far more complicated because we don't have amplitude, we don't really have midline, and we didn't spend as much time on tangent. So that's why I just do this with one transformation. So what I recommend is you look at the asymptotes. The asymptotes here are not drawn in, so I'm going to draw them in. So in between each full period, I'm going to draw these in. And the reason I like to look at the asymptotes first is because the asymptotes, if they're at pi/2 and negative pi/2, that's normal. All right, so if the asymptotes are in the normal spot, that rules out horizontal shift, because moving it left or right will change the asymptotes. It also rules out horizontal stretch or shrink, because the asymptotes are in the normal spot, the period did not change. So now we look at the graph and think, how does this compare to the original? So here's the one we're looking at. And if I were to draw the original in there, remember the original reminds me of x cubed. So that's my tangent graph right there. And I think we can see that we've reflected over the x-axis. So I would expect you to have this equation because you're thinking about a reflection over the x-axis. It did not say that you have to state the transformation. You just need to give an equation. But if you're thinking reflection over the x-axis, you'll have that. Technically, you could also get the same graph by reflecting over the y-axis. But we really didn't do too much with reflections over the y-axis because we found that we could get the same graph just by flipping over the x-axis, which is a little more familiar to us. Okay, so that's actually true for all of our trig functions. We didn't really do reflections over the y-axis for any of them, all right? Not just tangent. We didn't really do reflections over the y-axis for sine or cosine or secant or cosecant either. Okay, continuing on, we have some evaluate problems with inverses, like arc cosine, sine inverse, and arctan. This is from section 4.7. So the way that we learn to do this is we first acknowledge that we are looking for an angle, because for an inverse trig function, the ratio goes in, an angle comes out. So we're looking for an angle. Arc cosine's a little scary, so I changed to regular cosine, and I switched the input-output. So this is very similar to what we were doing back in number 4 and 5 on this worksheet. The only difference is because arc cosine is involved, we have to deal with the angle restriction for inverse cosine. So for inverse cosine, the angle restriction was 0 to pi. All right, so that means we can only use angles from 0 to pi. We cannot go into quadrants 3 or 4. So looking for where cosine is -1, that's not going to happen with 30 or 60 or 45 as a reference angle. That's going to happen at a quadrant angle. So if we test out each of these using the ordered pair that's on the terminal side, and I don't even have to bother checking down here because 3 pi over 2 is not within the angle restrictions. So I only have to check these 3. So where's cosine -1? Well, the definition of cosine is x over r. And for each of these r's, 1. If you're a unit circle person, you're skipping this because you're just going to look at the x. You're just going to look for where x matches, okay? But if you're using the definition x over r, you want to check 1 over 1. That doesn't work because it comes out to positive instead of negative. Check x over r, that's 0 over 1. That didn't work. And now check x over r here, that works. So the answer is pi. All right, and for these inverse trig ones where you're evaluating, there's only one answer. If you go back to earlier in the homework, when we were looking at, I switched colors. If you go back to earlier in the homework when we were solving, sometimes we get one answer, sometimes we get 2 answers. When you're doing the evaluate with the inverse trig functions, you only get one answer and it must be in radians because of our angle restrictions. Here's our next one. We're doing sine inverse of -1/2. That equals theta. So we want to switch that around because sine inverse makes me uncomfortable. So let's think of this as sine theta equals -1/2 instead. Because arc sine is involved or sine inverse is involved, we have to use the angle restrictions for arc sine, which go from -pi/2 to +pi/2. So for our drawing, instead of crossing out the 2 bottom quadrants, we cross out the left-hand side. So our angle can go to -pi/2 or it can go up to pi/2. It cannot go over into quadrant 2 or quadrant 3. So unit circle people, you will look at quadrants 1 and 4 and find where your y coordinate is -1/2. That's going to be at 11 pi/6. We'll join you in just a moment. For those of you who like your triangles, if you draw your 30, 60, 90, you'll find out that your reference angle is 30 degrees or pi/6. And then if all students take calculus and we already know we have to be in quadrant 1 or 4, sine is negative in quadrant 4. So we're all now in quadrant 4. looking at the angle that has a pi over 6 reference angle, all right, which we normally call 11 pi over 6. But this is that kind of problem where because of the angle restrictions, the absolute largest angle you're allowed to use here is pi over 2. You cannot use an angle bigger than pi over 2. And when you draw this, you go past pi over 2. It's too big. So what we need is a different name for this angle. We need a coterminal angle that's within those restrictions. So what we do is we just take this reference angle and we just put a negative on it. Because if we now think of this as negative pi over 6 instead, well, it's coterminal to 11 pi over 6, and it still has the correct reference angle, and it's within the restrictions. So we just use negative pi over 6 as our angle instead. Next one, arctangent of negative radical 3 equals theta. Okay, that's just my style because I like to acknowledge first that we're looking for an angle. Because for inverse trig functions, you put a ratio in, you get an angle out. And arctangent makes me uncomfortable, so I'm going to switch it over to tangent. All right, so because arctangent is involved, we have to use angle restrictions from negative pi over 2 to positive pi over 2, which is similar to the sine inverse restrictions. All right, so we have to eliminate quadrants 2 and 3. We have to eliminate the left-hand side here. We're only allowed to be over here on the right-hand side. All right, unit circle people, you're going to look for y over x comes out to negative radical 3, and that's going to happen at 5 pi over 3. We'll join you in just a moment there. For students who prefer your 30, 60, 90 or 45, 45, 90 right triangles, you're going to find that your reference angle for this one is 60 degrees, which is pi over 3. So looking at the quadrants that we have to choose from, if all students take calculus and tangent is negative, we need the answer in quadrant 4. So in quadrant 4, the angle that has a pi over 3 reference angle, we usually call it 5 pi over 3, but that's off limits because the largest angle we're allowed to use is pi over 2. So all we do is just kind of reverse the reference angle there and just find what's coterminal. What's coterminal to 5 pi over 3 is negative pi over 3. So that's the answer we're looking for. Okay, and then down here on the bottom, I threw in some verify algebraically examples for you to practice, and you can choose 2 of the 3. That's something I like to do when we're doing verify examples because I know it's easy to get stuck on these. So in the event that you're trying one and you get stuck, that just gives you the flexibility to say, all right, let me give up on that one. Let me go do another one and see if I can find an easier way to do it. All right, so if you choose A, we want to start with the more complicated side. I think that's this side. And if you think of your list of strategies, there's nothing to factor here. I'm going to put that barricade in. There's nothing to factor here. There's nothing to FOIL. There's no fractions to add. There's no fractions to separate. I really can't think of anything. There's no squareds. I don't have Pythagorean identities. So let's change everybody to sines and cosines. So to do that, let's make cotangent cosine over sine. And then you pause and you say, does that help? Is there anything I can do now? Yes, it does allow you to do something because what you have now is cosine times cosine over sine. So if you do top times top over bottom times bottom, you end up here. Now from this point, I think if you go back to your list of strategies, what you'll say is, oh, I have a fraction and I have something like that. If I make it a fraction, I can try to add fractions. So my LCD here is going to be sine. So if I want a common denominator here, it's going to be sine. So what I have to do in this first fraction is multiply by sine over sine. And that's going to give me sine squared over sine. And I need to show all my steps because remember, I told you the answer from the beginning. The answer we're trying to get is this. All right, so that's why I have to show all our steps. And then now that we have a common denominator, we can add the tops, keep the bottom, and hopefully, oops, not sine squared in the denominator, just sine in the denominator. When you're adding fractions, you keep the denominator the same. Don't change it, just add the tops, keep the bottom the same. And hopefully your eyes lit up when you saw sine squared plus cosine squared, because that's our basic Pythagorean identity. That's 1, which gives us 1 over sine x, which is exactly what we were trying to get. So that means we're finished. All right. That's not the only way to do this problem. But that's the way that I'm going to show here. If you did a different way and would like me to see it or want to me to check it over to make sure everything was allowed, let me know. I'd be happy to take a look at it. If you chose B, actually, I'm going to come back to B because there's two ways to do it. So I'm going to grab a separate piece of paper for that. Let me try C over here. Okay, so for C, the more complicated side is here, and we want this to be equal to 1. So I'm going to put that barrier in. That's to remind me that I can't like add on both sides or subtract on both sides or multiply on both sides or square both sides. And then I look at my list of strategies. I don't have Pythagorean identities because nothing's squared. I don't have fractions to add or separate. I don't have anything to factor, but I can FOIL here. I see 2 terms and 2 terms. So I'm going to FOIL. First times first is secant squared. The outers will be secant tangent. The inners will be minus tangent secant. I guess I shouldn't have put that barrier in yet because I need more space. All right. And then last times last is minus tan squared. Now, if you look, the inners and outers are going to cancel. If you don't see that they're going to cancel, I can help with that by writing an extra step. Okay. If you see that they're going to cancel, I'm okay with you jumping down to secant squared minus tangent squared. That's fine. But for anyone who's having a little difficulty seeing that, if I rewrite secant tangent here, so I'm going to copy that. If I just flip-flop the order here using the commutative property, I can make that secant times tangent. And that might help us to see, oh, that's an exact match. One's positive and one negative. That's why they cancel. Okay, so once again, if you can skip this step, I'm okay with that. All right, I know the directions say show all steps, but if you know that these are going to cancel, you can just cross them out. And then for secant squared minus tangent squared, that is 1. So you can replace that with 1 and you're all set, you're finished. The reason that is 1 is because we know that 1 plus tangent squared equals secant squared. That's on our list of Pythagorean identities. So when you're at this step and you have secant squared minus tangent squared, well, if you want to make that match, you can just move the tangent squared to the other side. And this, you're allowed to move back and forth on this because you know this one is true. We proved one of the Pythagorean identities, and then we derived the other one. So we know for sure this thing is true. That's why we're allowed to add and subtract on both sides. So if I move the tangent squared over, I have secant squared minus tangent squared equal to 1. So wherever I see secant squared minus tangent squared, I can replace that with 1. And that's what I wanted to get here. So that's how I know I'm finished with that one. This is not the only way to do the problem. This is just one way that I showed. So if you have a different way you'd like me to see, send me an email, send me your work. I'd be happy to look at your work and let you know if it's correct or help you along if you got stuck on it. Now I'm going to go back and do B. And I'm going to go ahead and just do that on the next page because I'm going to show this 2 different ways. So I wanted to make sure I had enough space for that. So I have cosecant squared theta minus 1 over cosecant squared theta. And that's supposed to come out to cosine squared theta. Okay, so when I look at this, the strategy that I immediately think of, because the top has 2 terms and the bottom has 1, is to split apart the fraction and make it cosecant squared over cosecant squared minus 1 over cosecant squared. This is 1. 1 over cosecant squared by a reciprocal identity is 1 minus sine squared. And we are really, really close to this because we just want cosine squared. This is cosine squared. If you can look at your Pythagorean identities and just know that that's equivalent, then you don't have to show the side work. Okay, and once again, I know I say show all steps, but it is okay with me because I do believe it that you might be able to look at this in your notes and say, oh, okay, so if I have 1 minus sine squared, you can visualize moving the sine squared over, and you know that's going to leave you with cosine squared. All right, so you don't have to show the side work. But if you want to, what you would do here is you would show that you are moving sine squared over. And then you now know that anytime you see 1 minus sine squared, you can replace it with cosine squared, and that's what we wanted. So that's one way to do the problem. It's not the only way. There are many, many ways. And here's another way to do B. If you have cosecant squared theta plus 1. Oh, was that minus? Okay, that was minus. Okay. Over cosecant squared theta another way to do it, which is not what I see immediately. So I immediately see to split this apart, but some of you are going to look at this and see immediately that you have a Pythagorean identity up top because you recognize the squared and the 1. So if you have 1 plus cotangent squared equals cosecant squared, that's in your notes. That's a Pythagorean identity. We know this is true, all right, because we derived that from something that we proved. So we know this is true. So you can move stuff around left to right as much as you want over here, okay? For this one, you can't cross that barrier because your job is to prove these are equal. So you can't multiply both sides by cosecant squared or anything like that. But this one you know is true, so you feel free to move things around all you want. We have cosecant squared minus 1 up here. So to make that match, I'm going to slide the 1 over. And anywhere we see cosecant squared minus 1, we can replace with cotangent squared. So I'm going to replace these two terms with cotangent squared. And I think the reason I like the other method a little better is because I have to create a complex fraction in my next step. And I don't know, I personally try to avoid that. But when you're at this step right here, you kind of don't have anything to do except change everything to sines and cosines. So for cotangent squared, it's going to be cosine squared over sine squared. And a lot of you might not mind the complex fraction. I don't know, just makes me a little uncomfortable. And I do try to make that fraction bar like kind of extra big to make sure I see that this is my top and this is my bottom. So cotangent squared becomes cosine squared over sine squared, and cosecant squared becomes 1 over sine squared. There are many different ways to simplify this. The favorite way usually of my students is instead of dividing by 1 over sine squared, you like to multiply by the reciprocal, which you often call same change flip. So keep that the same, change to multiplication, flip the fraction. And then what happens is sine squared over sine squared reduces, leaving you with cosine squared, which is what we wanted. So it's a completely valid way to do it. And by the way, in terms of, I've said you have to show all steps. If you leave out this step, I'm okay, because I believe that you know that if you have this divided by this, it becomes cosine squared over sine squared times the reciprocal. So you can show this step or not show the step. I'm okay with that either way. And once again, there are many other ways to complete this example B or number B. So if you have a different way that you'd like me to see, drop me an email, send the work. I'd be happy to take a look at it or give you hints if you got stuck on it, help you if you got stuck on it, whatever you need. All right. Thanks, guys. Hope that helped.